Is that okay?
Yes.
Okay. Today I'm going to talk about linear and nonlinear phenomena in black holes. Binary black hole coalescence is likely the most violent astrophysical process that can trigger rich linear and nonlinear phenomena in black hole spacetime. After a decade since the first event, GW 150914, we have detected hundreds of gravitational waves from merging binary black holes. For a typical system, there are 3 stages involved, including in spiral part, merger part, and the random part. And so far, numerical relativity still remains the only first principle approach to track the whole evolution process and to produce accurate gravitational waves. But nevertheless, people have developed some analytic tools such as post-Newtonian theory and black hole perturbation theory to gain some physical insights into different dynamical regimes. Especially the random part corresponds to the oscillation of the remnant black hole, and the emitted gravitational wave is largely consistent with the superposition of the so-called quasi-normal modes, whose complex frequencies are determined by the mass and spin of the remnant due to the no-here theorem. And in the following, my discussions will be rooted in this perturbative perspective. I will be covering 2 major aspects, the nonlinear part and the linear part. For the nonlinear portion, I will specifically talk about mode coupling and dynamical nonlinearities. All right, so let's get started. Feel free to stop me anytime if you have any questions. Quadratic quasi-normal modes are likely the simplest objects that reflect the nonlinear features of general relativity. In short, it is a second-order effect of a quasi-normal mode. Let's here imagine a linear mode H goes as e to minus omega t. This mode carries energy and orbital angular momentum, which can lead to an effective stress energy tensor and further perturb the spacetime geometry. And roughly speaking, its source is given by h squared. So we can imagine that the spacetime will undergo a driven oscillation at 2 omega. And the amplitude is proportional to a squared. The coefficient in front of it, which we refer to as the excitation factor, capture the intrinsic nonlinear features of a pure black hole. Why do we care about quadratic quasi-normal modes? First, like I mentioned, they are the nonlinear features of general relativity, but maybe they are simple enough that we can develop analytic tools to handle them. This is in sharp contrast to some other general nonlinearities, such as the merger part of binary black hole merger. In that case, we have to rely on numerical relativity and treat it as a black box. There is no available analytic tool. And finally, although the quadratic modes are sourced nonlinearly, they still enter the gravitational wave in the same way as those linear quasi-normal modes. So there is no need to design new analysis tools to study them. We can just rely on some existing quasi-normal mode fitting methods. By using a black hole second-order perturbation theory, we found that for a single quasi-normal mode, it can be sourced by some multiple channels. This diagram shows the simplest one. So imagine we have 2 linear parent modes, omega 1 and omega 2. Their coupling can lead to this summed frequency, omega 1 plus omega 2. But this is not the end of story. The subtlety, there are a few other channels which are more subtle. The subtlety comes from that for a given quasi-normal mode, it is always accompanied with a mirrored frequency channel. Here, for example, let's imagine we have a psi4 contains a single quasi-normal mode, and in its metric data, h mu nu, because this is a real number, it has 2 frequency components. the first one is the original one, and the first one is its complex conjugate. So this second one is called the mirrored channel. So here, let's imagine we have the third parent mode, psi minus 2 bar, whose frequency is at minus omega 2 bar. Here, this bar means complex conjugate. Notice that this psi minus 2 bar is a different parent mode from psi 2 itself represents an independent quasi-normal mode. Because of this mirrored channel, psi minus 2 bar can generate a frequency component in its metric at omega 2, which can couple with the first quasi-normal mode omega 1 and leads to the excitation of the same quadratic mode. And similarly, we can exchange the rho between 1 and 2, and this brings us to the third channel. And finally, we have the coupling between those two barred modes. So in the end, for a given quadratic mode, it is sourced by 4 channels, and there are 4 parent modes involved. Oh, sorry. Based on this, we can sort of formulate some Feynman rules in the sense that the quadratic mode amplitude can be written as a coupling constant multiplied by the corresponding parent mode amplitude. For example, in this case, this channel can lead to a quadratic mode with amplitude given by this constant C++ multiplied amplitude of omega 1 and omega 2. For the remaining 3 channels, we have parent modes which belong to the mirrored branch. So we need to first take complex conjugate first. For example, in this case, this minus omega 2 amplitude is given by A minus 2. We need to first take a bar for that. And whenever we do this, we use a minus sign in the subscript to track this operation. So in the end, we have plus, minus, plus, and minus 4 channels. Putting all those 4 channels together, the total quadratic amplitude is given by the sum of all of them. So here, as you can see, those 4 coupling constants are really the fundamental quantities that reflect the nonlinear features or nonlinear responses of a curved black hole. So it would be interesting to compute them from the first principle. Here, to achieve this goal, we adopt the black hole second-order perturbation theory. The whole calculation steps are quite involved. So instead, here I just want to give overall. I just want to highlight the overall workflow. So imagine we have a linear quasi-normal mode represented by this well scalar psi4. Then we can construct the corresponding Hertz potential. Then working within the outer radiation gauge, we can do the metric reconstruction to construct all the metric components for this quasi-normal mode. Then using the commutation relations and the Ricci identities, we can build the quantities in the Newman-Pearls formalisms. Then with all those established variables, we can extract the full source term for the second-order Tokosky equation. And finally, we just solve this equation to obtain those coupling coefficients. It turns out that those coupling coefficients, they depend only on the dimensionless spin of the black hole. And remarkably, we found that this minus channel always vanishes, regardless of chi and the choice of the parent modes we pick. At the beginning, we found this behavior fully numerically, and very recently, we are using, with the help of AI, we are able to convert this analytically, but we still don't know whether there is any deeper physical reason or deeper physical symmetry behind it that make this constant always vanishes.
In some sense, there's nothing special between plus and minus. If I change my convention, how do I define this relative harmonic? So it is one of the two of these here, right?
No, actually, no. So imagine you have a single mode. This mirrored channel is always special, right? So this is not present in psi4. Sure. So you always have a special component. Yeah, right. But again, this number always vanish. We don't know whether there's any different reason. Apart from this first principle calculation, there is a complementary strategy which is fully data driven. So in this case, we can send a Gaussian gravitational packet into a black hole and then evolve the system using full 3+1 numerical relativity. Then we can measure the gravitational waves at future null infinity to extract all those coupling coefficients. So both methods should give consistent results, and indeed they do. So in this figure, this gray curve, this gray curve is the analytic result that we computed with black hole second order perturbation theory as a function of black hole's dimensionless spin chi from 0 all the way to 1. And meanwhile, those scattered points with error bars, they are measured from those numerical experiments. So you can see that they are both of them agree, both of them are consistent, and they follow the same spin dependence. So actually, this example gives a good this comparison gives a good example to demonstrate the success of black hole second order perturbation theory. All right, so that's a basic picture for the quadratic quasi-normal mode. Let's take a step back and reveal the physical insight behind this. Schematically, the black hole dynamics is given by the Tokosky equation driven by a nonlinear source, and importantly, the left-hand side is identical to the linear operator. So the total the whole nonlinear effects completely enter through this nonlinear source term. Here we can think of this source as a tidal field acting on the black hole, and the corresponding particular solution can be thought of as the tidal response, which is related to the tidal field by a sort of through a set of quote-unquote Wilson coefficients. And here we can compare this pattern with the quadratic quasi-normal mode that I introduced. And apparently you can see that those coefficients that I mentioned earlier, they are basically the nonlinear Wilson coefficients of a curved black hole. From this perspective, quadratic quasi-normal mode, it is an adiabatic nonlinearity in the sense that once we provide a pair of parent modes in terms of their amplitudes, the following tidal response is fully determined by those constants. So they don't have their own dynamics. So based on this, in parallel of this adiabatic nonlinearity, as we can imagine, there has to be other class of nonlinearity which is supposed to be more dynamical. This is similar to dynamical tide in neutron star or in exoplanets. So this dynamical response can be triggered when the time scale of the tidal field matches the intrinsic time scales of the system. And in this case, the response is no longer adiabatic. Instead, they can have their own dynamics. The resonance is one good example. So let's consider one example. Let's consider a toy model. This is the example that Niels used yesterday. So here we have a Tokosky operator with a nonlinear source. And in the initial data, we can set it to be a pure 2-to-0 quasi-normal mode. And because of this nonlinear source, it can generate a frequency component whose value is very close to the first overtone 2-to-1. This plot shows the relative error between this frequency component and the 2-to-1. And as you can see, the relative error is always on the order of a few percent, and it vanishes in the extremal limit. So here, as you can imagine, the 2-to-1 first overtone can be resonantly excited by this fundamental mode through this nonlinear coupling. The second example is the parametric resonance. Let's imagine we have some nonlinearity, and this nonlinearity introduce some time-dependent dependence to the background. And when this time scale matches the black hole quasi-normal mode frequencies, there could be parametric resonance. And the examples are given by Yang and collaborators back in 2015. And finally, I would like to highlight other class of dynamical response, which is called traveling wave resonance. This resonance is by nature very different from the first mode resonance. In the first case, we need to have resonance when the driven frequency matches some internal eigenfrequencies of the system. However, there is no such requirement in the traveling wave resonance. Let's again consider a toy model. This is a plane wave. This is a 1D plane wave, a 1D wave equation driven by a traveling wave. And its particular solution is given by t times e2 I omega times t minus x. So this t factor says that this wave equation is always resonantly excited. And very importantly, here you can see the left. This flat spacetime doesn't have any internal eigenfrequencies. And so as a result, this omega can take any real value. Here we can understand this feature by borrowing some insights from field theory. In that case, each spatial location will have a local harmonic oscillator, and those oscillators talk to each other through this spatial derivative. In the presence of this traveling wave, it can coherently trigger the excitation of those neighboring harmonic oscillators and lead to a cumulative growth in psi. So those are a few examples for the dynamical nonlinearity in black hole spacetime. Below, I'm going to show you how to use numerical relativity to reveal some of these dynamical nonlinearities. As we know, in the literature, the most common approach to exact nonlinear phenomenon in black hole spacetime is to establish some initial data containing some gravitational packets, and then we can send this packet into a black hole to trigger some nonlinear phenomenon. But this approach has some caveats. First, we always need to solve the constraint equations to construct the initial data. This can be subtle and it can be difficult when this pulse is strong enough. And second, this packet is always spatially compact. As a result, the pulse always triggers a transient effect. The nonlinear interaction always happens within the scattering timescale. And after that timescale, the system quickly transitions to the linear rain-down stage. So for our purposes, we would like the nonlinearity to happen over a longer timescale. It's something that initial data itself cannot really handle. So to fix this, we design an alternative strategy to study this. So instead of using initial data, we change boundary conditions such that we can inject gravitational waves into a system. And in our setup, we can specify this gravitational wave to be any function of t and time and the spatial coordinates at the boundary without introducing any constraint violation. As a result, we can actually change those gravitational waves when the simulation proceeds. For example, we can inject a gravitational wave for some time, then turn it off and then turn it back on after a while. Or we can inject continuous gravitational waves into a system. This is analogous with using a spoon to keep stirring a bottle of water. When the fluid is driven continuously, some nonlinear mechanisms behind that could trigger energy cascades across scales and generate small eddies due to this direct turbulent cascade. Here we hope that the same intuition could apply to the gravity scenario as well. If we continue to use the gravitational wave to stir a spacetime, maybe nonlinearity could build up and lead to some interesting phenomena. This is our numerical setup. Here we shoot a continuous wave into a Schwarzschild black hole at a far distance. We do this by specifying the Weyl scalar psi4 at the outer boundary. Here, this psi4 is decomposed into the spin-weighted spherical harmonics and multiplied by a time-dependent function. And in our case, we just set it to be a monochromatic sinusoidal wave. And in each experiment, we fix the angular pattern as well as the frequency value. And finally, we monitor the dynamics on the apparent horizon. Okay, so the first obvious nonlinear phenomenon that we saw is the frequency-dependent mass accretion. This plot, this top panel, shows how a black hole mass changes with time. Let's first look at this dark blue curve. In this case, we can see that the mass grows linearly in time, which implies that the black hole enters a steady accretion state. The accretion rate m dot is proportional to the injection amplitude squared. And the coefficient in front of it is frequency dependent. This frequency dependence arises because the transmissivity of the black hole potential barrier depends on the frequency. Because we are injecting gravitational wave at a far distance, and it needs to penetrate this potential barrier in order to be accreted. That's how this frequency dependence kicks in. Now let's go back to this figure again. In this panel, it shows the transmissivity as a function of omega times m. In the low frequency range, you can see the transmissivity is almost 0. And it gradually, the black hole becomes gradually transparent when omega goes to a larger value, and eventually it asymptotes to unity. So as a result, we can look at this. We can look at this light blue curve. This is especially interesting. At the beginning, we inject a wave at a low frequency. So the transmissivity of the system is quite low, and you can see that the black hole barely accretes mass. But over time, this black hole becomes a little bit large. Then the effective frequency seen by this black hole, which is controlled by omega times m, this combination becomes bigger. Then the system transitions to the high transmissivity regime, and it becomes more efficient for the black hole to observe the energy. So eventually you can see that the accretion slope becomes bigger than its initial stage. In our most nonlinear setup, this black hole can become 6 times bigger. All right, so now let's take a look at the response on the apparent horizon. In this setup, we set this gravitational wave to be a monochromatic wave with 2-0 angular pattern. This wave can trigger a bunch of responses on the apparent horizon. Here, this plot shows each angular and frequency component as a function of time. In the top panel, we have the first order linear response. This is the omega component in the 2-0 harmonic. And we have confirmed that its profile scales with the injection amplitude A. So indeed, it's the first order effect. To the second order, we have 2 omega in the 4-0 harmonic. And this is analogous with the quadratic Poisson mode that I introduced. Again, we confirm that its profile scales with A squared. And finally, we found 2 third-order components in 6-0 harmonic, including omega and 3 omega. Both of their amplitudes scale with A cube. Schematically, this omega is equal to omega plus omega minus omega, and the 3 omega is equal to the sum of 3 omegas. So far, those excitations are quite typical nonlinearities that we are familiar with. They are adiabatic in the sense that once they are excited, they just stay here. They don't develop additional dynamics, and their amplitudes are completely fixed by a to some power multiplied by some constants. However, if we repeat this experiment with bigger and bigger injection amplitude, something much more interesting could happen. Here, this plot shows the evolution of a few frequency and angular components as a function of time. Here we have a few injection amplitudes as indicated by the different colors. For weak driving, for example, in this case, once the modes are excited, they just stay here, right? So they just stay here. But when A increases, we can see that those modes undergo the secondary excitation, followed by saturation and a decline. Right? So we always see this feature in in all those modes. The bigger the injection amplitude we choose, the earlier this secondary excitation happens. We found that the growth rate skews with A cube, and the saturation amplitude skews with A to the first power. Those excitations are by nature very different from the early adiabatic responses, because in this case, those modes have their own dynamics. They can exchange energy between each other, can have this growth, saturation, and then a decline. So they are adiabatic responses. To better see this, we can look at this time frequency plot. And again, let's focus on the response in the 6-0 harmonic. At the very beginning, we have the excitation. We have two third-order modes excited. So we have 1 omega and 3 omega. And after some time, this 2 omega is excited, and then it's saturated and goes away. And then after a while, this omega undergoes a similar dynamics. If we use this yellow dashed arrow to connect all those three stages, we can see a very clear pattern. Here, this 3 omega behaves as a major energy budget to fit the excitation of the following frequency components. And here we can see that the underlying nonlinear mechanisms features an inverse cascade. The coupling tends to transfer the energy inversely down to lower frequencies. We also see similar responses in 4-0 and 2-0 harmonics. As for the 4-0 on the left, we have the dominant excitation initially at 2 omega. This is analogous with the quadratic quasi-normal mode. And after some time, this omega is excited. And we can, again, rely on the intuition that we have. This omega behaves as a major energy budget to source the following excitation in omega component. And finally, in the 2-0 harmonic, we have this first order response at omega. But in this case, there is no available lower frequency slots for the energy to cascade. So this component just stays here and gradually decays away. So far, I have focused on Schwarzschild spacetime. If the black hole has a spin, the story could become a little bit different. Let's again look at the response in the 6-0 harmonic. Remember that in the Schwarzschild case, we have two dominant third-order modes, omega and 3 omega. Because in this case, 3 omega is stronger than omega, it can become the major energy budget to trigger the following excitations. However, when black hole has a spin, let's see 0.7, omega actually becomes bigger than 3 omega. Then in this case, 3 omega stops to behave as a major energy source. And for the omega, because there is no available lower frequency components for the energy to flow, it just stays here and goes away. There is no available, there is no subsequent secondary excitations anymore. Okay, so that's the basic story when we inject 6-0 harmonics, 6-0 gravitational waves. I think the major takeaway message is that the nonlinear mechanisms in general relativity tend to transfer the energy inversely down to lower frequencies. Then this raises an interesting question. How about the angular part? Could we observe similar dynamics as well? So to study this, we inject 6-0 gravitational waves into a spacetime, and again we see a bunch of mode excitation. In the 6-0 harmonic, we have this omega component, which arises as a first order effect. Its amplitude scales with A, and we also have this second order mode 2 omega. Which comes from the second order coupling, its amplitude scales with A squared. We also found this 2 omega in 2-0 harmonic and 4-0 harmonic, both of them second order effect. And as you can see from those black curves, once those modes are excited, they just stay here without undergoing additional dynamics. So they are adiabatic. But more interestingly, we can see that there is also omega component excited in 2-0 and 4-0. Their amplitude grows linearly in time, and the slope is proportional to A cube. So it implies that the omega component undergoes third order resonance. And more interestingly, we found that we also found similar nonlinear resonance in flat spacetime. So this implies that this resonance is not tied to any eigenfrequencies of the system. So this aligns quite well with the traveling wave resonance that I introduced earlier. In the presence of a traveling wave, we can have this resonant solution. Finally, this plot is the mode amplitude as a function of angular harmonic measured at different times. The darker blue means later time. So this is our injection. Initially, they have comparable amplitude, but because of this nonlinear resonance, their amplitude grow linearly in time, and eventually they become bigger, stronger than this injected amplitude. And so we can see that the gravity also tends to transfer energy down to larger angular structure. So that concludes the first part of the talk, which is about nonlinearity. Before moving on, is there any question? Quick question. If not, okay. So let's move on to the second part, which is about some linear response in black hole spacetime. To begin with, let's recall the numerical setup that I used to study these dynamical nonlinearities. In this case, we modify boundary conditions to inject gravitational waves into our simulation domain. In fact, this methodology is a part of a bigger topic in numerical relativity. As we know, the most common approach in numerical relativity to solve Einstein's field equations is to adopt this Cauchy approach. The basic idea is to split the spacetime into three-dimensional spatial slices as a one-dimensional time direction. As the name implies, we can convert the system to a Cauchy problem by providing some initial data on the first slice and some boundary conditions. We can evolve the metric data forward in time, step by step. For example, in this case, we can put two black holes in an orbit on the first slice and numerically evolve the system to let them in spiral and merge and emit gravitational waves. At the outer boundary, gravitational waves are mainly outgoing. So people normally pick transparent boundary condition to avoid reflection at the boundary. But is that sufficient? The answer is no. It's not sufficient for general setup. To give you an idea, let's consider a toy model. Here we have a binary black hole system on the left, and this is our outer boundary. As the system evolves, it emits gravitational waves outward. Some gravitational waves that have already passed through the outer boundary can be reflected by the local spacetime curvature and re-enter the simulation domain again. Right now, this transparent boundary condition is not able to capture this backscattered effect. So in order to really simulate this inner region in an exact manner, we really need to prescribe how this backscatter wave evolve over time. It turns out that this is a very hard problem. So right now, people just ignore this piece from current simulations. Luckily, this backscatter effect decays very quickly with the outer boundary. So in principle, one can put this outer boundary far enough to avoid this problem. But this is really a stopgap solution. It only works for some short simulations, and it makes the simulation unnecessarily expensive. So in order to fix this issue from the first principle, we really need to design a different formulation to handle the outer wave zone in order to predict the backscattered gravitational wave. So far, there are a few formulations in numerical relativity, including the Cauchy evolution, which can handle the near zone, the characteristic evolution, which is suitable for the wave zone, and maybe there are a few formulations which can handle both zones simultaneously. And for our purposes, we could just use this characteristic evolution to compute the backscattered effect. The basic idea of the characteristic evolution is to adopt different slices for evolving Einstein field equations. Slices mean observers. Those Cauchy slices correspond to time-lag observers who sit at different spatial locations, and they are synchronized by those space-lag hypersurfaces. And during a simulation, we track each observer and see how the metric data evolve with the local time. However, for the characteristic evolution, we instead formulate the space-time using those null rays generated by outgoing null radiation. So here, as you can imagine, this is more suitable for radiation propagation. Those observers are organized by those null slices, and the simulation marches toward this direction. By using those null slices, one can rewrite the Einstein field equations using a bounded X coordinate system, which brings us to the so-called characteristic formulation, which we can use to handle the dynamics in the wave zone. So in practice, we can put both Cauchy and characteristic systems together to handle both near zone and the wave zone simultaneously. And in this setup, we sent outgoing modes from Cauchy to characteristic to evolve the outer wave zone on a single time slice. Once this is done, we can send the backscattered modes from characteristic to Cauchy to construct the exact boundary condition, including the backscattering waves. In other words, we match those two systems together and evolve them at the same pace. So this method is called Cauchy characteristic matching, or CCM. And here you can see that an important step to achieve CCM is to inject the backscattered radiation as computed from the characteristic side into the Cauchy side. And this is exactly the tool that I used to study this dynamical nonlinearity. So after my years of development, right now this CCM has become a quite mature method, and we can use CCM to merge binary black holes quite routinely. And below, I'm going to show you an important application of CCM, which is to review late-time power law tails. As we know, those tails come from the backscattering of gravitational waves of large-scale space-time curvature. So if we want an algorithm to pick this infrared structure, we really need this algorithm to cover the entire simulation domain. And this is exactly what CCM is good at. So in this example, I use CCM to merge a binary black hole system whose parameters are chosen to be consistent with the first gravitational wave event, GW150914. This is the psi4 as a function of retarded time extracted at future null infinity. Apparently, you can see a very clean tail at late time. And this is, in fact, the first time we are able to run CCM on BBH mergers, and we are able to resolve tails in the fully nonlinear regime. If we do not use CCM, we will instead get this blue curve. So in this case, we can see that there is a huge systematic error at late times, and those errors are completely caused by the wrong boundary conditions because they are gone if we push the outer boundary far enough. Right. So, but you see, the CCM is able to pick up the correct tail even when the outer boundary is close, very close to the system. All right, so that's the basic story for CCM and the tail. Is there any questions so far? Yeah. The decay rate is around minus 3.5-ish in psi4. Here L is equals to 2. We can chat more of that. Okay, so the final part is about the near horizon source-driven emission. As I have mentioned a few times, the black hole dynamics are governed by this Tolkowsky equation with a source term. A useful approach to obtain this solution is to use the Green function method. So the total solution is given by the Green function convoluted with the source term. Here, as a result, as you can see, the total waveform is contributed not only by the Green function, including quasi-normal modes and the tail. There is also a piece contributed by the source term. And I believe Laura will also talk about this in her talk. Especially when this source moves very close to horizon, there will be some interesting imprints on the gravitational waves. So let's imagine we have a small particle gradually falls into a central black hole along this black trajectory. At the early in-spiral stage, it triggers gravitational waves directly toward observers. So this regime can be described by the post-Newtonian theory. Once the black hole, once this particle gets close to the photon ring, quasi-normal modes are excited. But this is not the end of story. Even during and after this regime, this small particle still continues to behave as a source to trigger the source-driven emission. You know, this source-driven emission from the very early in-spiral stage all the way up to the very late stage, they should evolve continuously. It is not shut down abruptly. Here I use those gray arrows to indicate this near horizon source-driven emission. Because they are sourced very close to the horizon, they actually carry some near horizon features. There are two important features that we need to consider, including the fringe juggling effect and the redshift effect. As we know, when the central black hole rotates, it can push the nearby spacetime and push the nearby to drive the nearby spacetime and push the particle to co-rotate with it. As a result, the emitted source-driven emission should oscillate at some frequencies to reflect this fringe juggling effect. And meanwhile, Once this wave is sourced, it needs to climb the potential barrier in order to escape to infinity. That's where this redshift effect kicks in. And this redshift effect makes the wave becomes weaker and weaker as the particle gets closer and closer to the horizon. And the decay rate is controlled by how fast this particle gets to the horizon. To give you an example, here we can look at numerical relativity waveform. This gray curve is the numerical relativity 2-2 harmonic from numerical relativity simulated for a GW1509-14-like system. Apparently, you can see quite clean late in spiral merge and rain down stage. Using a method to remove those quasi-normal modes, we obtain this black curve. And you can see that there are a few oscillations over here which look like a mode, but they don't belong to any quasi-normal modes. And it turns out that those few cycles are sourced in the neighborhood of horizon. Why is that the case? Because in our previous paper, we use a theory to develop an analytic model, which is shown as this black curve, black dashed curve, and the agreement is fairly well. So this gives us some sort of confidence that those cycles are sourced in the neighborhood of horizon. And currently, I'm able to develop some solid theoretical method to put this phenomenon on a very solid background, at least for memory in structured spacetime. After reviewing this signature from numerical relativity, it is also interesting to see whether we can observe this part from real observational data. So on January 14th, 2025, the LIGO Virgo Kagura collaboration observed is the largest gravitational wave event to date. This noisy gray curve is the raw data after whitening. Because this event is so loud, we can actually see the gravitational cycles, especially the late rain down stage. And by the way, this red curve is the best fit from numerical relativity waveforms. Then we use some data analysis pipelines that we developed to subtract quasi-normal modes, and we obtain this middle panel. You can see that those quasi-normal mode cycles, those quasi-normal mode cycles are basically gone. You see, in original signal, there are some quasi-normal mode cycles, but then in the middle panel, those cycles are basically gone, and we are left with this heartbeat-shaped pulse. The late part is emitted from this near horizon region. And using our analytic tool, we can do a Bayesian analysis, and we can further subtract this component from the middle panel, and this gives us to this bottom panel. So again, in this case, those cycles are gone. So this suggests that the data are consistent with our theoretical interpretation. We can also extract the frequency and the decay rate from those few cycles. Those contours are the 90% credible region that we extracted from that time window, from that wave component with different starting time. Here, our start time range from -9 all the way up to -3. At the beginning, you can see that the posteriors still evolve a little bit. This is because the particle still undergoes dynamical evolution in the neighborhood of black hole horizon. But they all cluster around this red region, which is so-called horizon mode. For this horizon mode, its frequency is around 2 omega h, where omega h is the horizon rotation frequency, and the decay rate is the horizon surface gravity kappa. So here, by analyzing this event, we can really use real observational data to touch the near horizon region. It is quite cool, isn't it? So here I don't have more time to jump into technical details. So feel free to wait for our paper, which will appear in Nature very soon. So actually, this is my last slide. So to summarize, in this talk, I covered a few nonlinear phenomena, including mode nonlinearity and also dynamical nonlinearity. I also mentioned Cauchy characteristic matching, and using this method, we can review tail from merging binary black holes in the fully nonlinear region. And finally, we are able to identify this near horizon source-driven emission, not only in numerical relativity waveform, but also in real observational data. Right now, our theoretical development for this source-driven emission is still ongoing, and I would like to highlight that right now we are developing some AI agent to basically completely handle all the theoretical calculations related to black hole perturbation theory. And with that, let me stop here and take any questions.
When you were talking about nonlinearities and this wave injection,